In the first and second parts of this video lecture, we have seen the definition of conditional expectation as a function that whose value can be determined if we know the information related to a sigma algebra G. This is not a very precise notion at this point. It's just some intuition to understand that G is a random variable which is more coarse than X, and it is the best approximation that we can make for X if we only have access to the information on this sigma algebra, in the sense that its average coincides with the average of X for all set that is measurable, for, let's say, for all events that can be determined from the sigma algebra G. Then we made this remark about the conditional expectation being unique in the almost sure sense. And then we discussed, to get some more concrete example, what would be the conditional expectation with respect to the sigma algebra G if the sigma algebra G is generated by a partition. Okay, so here is the picture of a sample space partitioned. These green lines partition it into finitely many or countably many pieces. And then what is the conditional expectation of X given this partition, or given the sigma algebra generated by this partition? Well, it is a random variable which is constant in blocks of this partition, in elementary blocks of the partition. It's constant and takes this value there, the average value of X. Then we stated the theorem saying that if the expectation of X is defined and X is almost surely finite, then the conditional expectation of X given G exists. And now we move into the proof. We start assuming that X is non-negative and integrable. We consider this case first because later on we're going to resort back to this case when we consider more and more general cases. So suppose that X is integrable and non-negative, and we're going to define a measure nu on this measurable space. Okay, we're taking a different space. We consider things coarser sigma algebra, and we're defining the measure of the measure nu. This measure nu, it doesn't have so much meaning. It's just a tool that we use in the proof. So we define this measure nu to be exactly the measure that has density X with respect to the probability measure. Okay, so this we can recognize this expression. That's why we're presenting this notion of conditional expectation in this chapter. This is really defining a new measure from an old measure in terms of an integral. And well, we're assuming first that X is integrable, which means if we put omega here instead of A, then this integral is finite. So the measure nu of the set omega will be the expectation of X, and this is finite by assumption. And in particular, nu is a sigma finite. Why do we want nu to be sigma finite? Why do we want nu to be sigma finite? Well, because if we come back here to the previous video lecture, we want to apply the Radon-Nikodym theorem, and the Radon-Nikodym theorem requires both measures to be sigma finite. It also requires that the second measure be absolutely continuous with respect to the first measure, and this is also something we have to check. But if we come back here to our definition, we defined already nu to have a density with respect we define nu to have this to be given by this integral, and this integral, it is will always be zero if we plug in here a set A that has a measure 0. So it is then true that whenever the probability of A is 0, then the measure nu of A will also be 0. And because of that, I said X is a density, but that's not really accurate. Just because we have X here, it doesn't mean X is a density, because X is not a measurable function on this measure space. That's the whole point. X is not a measurable function on this measure space. And because X is not a measurable function on this measure space, we want to take a measurable function that approximates X on this space. Okay, so this integral here is with respect to P, but on this probability space. So in order to compute this integral, this computation is done in this world here, where F is the sigma algebra. Okay? Except that, well, we're doing the computation on a space where F is the sigma algebra, but we are restricting this computation for sets A, which happen to be also not only in F, but also in G. Okay, and so X is not really the density. We now use the Radon-Nikodym theorem to say the density exists. And again, the density, it cannot be X, or it may not be X, because we're not assuming that X is G measurable. And we're applying Radon-Nikodym theorem on this measure space here. We know that if omega F P is a measure space, we know that we can replace F by another sigma algebra smaller than F, let's call it G, and this will still give us a measure. Okay, and we're applying Radon-Nikodym theorem on this measure space, and we're getting a derivative, a Radon-Nikodym derivative, which is measurable with respect to G. Okay, so it's quite subtle how we are applying Radon-Nikodym theorem here. Okay. Now we define Z to be nothing but that Radon-Nikodym derivative. And note that X will satisfy the two conditions for being the conditional expectation. The first condition, Z is G measurable. This is true. Why is this true? Well, because we are applying Radon-Nikodym theorem. Let's put here a big level of separation here. We are applying Radon-Nikodym theorem on this space. When we apply the theorem, we completely disconsider the fact that this function here was computed using a probability space with a different sigma algebra. Okay? The theorem doesn't need to worry about that. All we want is to know that nu is a measure on this space, on this measurable space, and nu is absolutely continuous with respect to P. Well, not exactly P, the restriction of P to this sigma algebra again. So we can use Radon-Nikodym theorem here. This will give us a variable that is G measurable, and by construction, this will give us a random variable that satisfies the condition. The integral on A of Z dP equals the integral on A of X dP for every A in the sigma algebra G. And why is that? Well, because this is exactly nu of A, and this is exactly what Radon-Nikodym theorem gives us.